Alright, so we are still on applied mechanics for engineers, and we are considering the topic equilibrium of bodies in space. Equilibrium of bodies in space. So this is the second question. We have a diagram like this. This is a cylinder, and this shows you the weight of the cylinder. Okay, and these are the dimensions: cable AD, cable AC, and cable AB. Alright, so take note of this diagram, observe the diagram carefully, and look at their dimensions. Okay, then the question says a container is supported by three cables that are attached to a ceiling as shown. Determine the weight W of the container, knowing that the tension in cable AB is 6 kilonewton. That is the tension in this cable AB is 6 kilonewton. So take note of that. Alright, then we'll then draw the free body diagram. Draw the free body diagram from this figure given to us, and we'll be having something like this. This is our free body diagram, and this is showing you the weight that is acting vertically downwards. Okay, the coordinates are I with respect to the x-axis, coordinate J with respect to the y-axis, and coordinate K with respect to the z-axis. Alright, and then this is tension vector TAB, and the position, the unit vector is lambda AB, and this one is vector TAC, the unit vector is lambda AC, and this is vector TAD, the unit vector is lambda AD, and these are their dimensions. Okay, we'll make use of this in finding the distance RAC, RAB, and RAD. Okay, so let's solve this question. This is the free body diagram. Okay, so we will then take the first equilibrium condition. The first equilibrium condition is to take the resultant of all the forces. Resultant of all the forces, and then that is arrow equals to sigma F, which is equal to, okay, let's take all the forces. First is tension AB plus tension in the cable AC, tension AC. Okay, that's the vector TAC plus, we take the vector TAD plus the vector weight, the weight there, which is also a vector. Okay, and then I think those are the only forces there. They are the only forces there in that free body diagram. Okay, right, so we have something like this. We can call this one equation 1. We can call this equation 1. Okay, so those are the forces, this tension here, and the weight. Okay, which we can call equation 1. Now the next thing we will consider, we'll first consider cable AB. So consider cable AB. Okay, so we'll look at cable AB, and we are going to get the distance RAB. So this now, okay, so I've showed you the movement is with respect to I, J, and K. So anyone that is going with respect to I is positive I, going up with respect to J is positive J, going like this is positive K, but if it is going opposite direction, it will be negative. Okay, so let's move. So if I move now like this, if I go up here, I'll be having from here like this, I'll go up to this point, move to this point, I'll have what? Plus 600 J. Okay, so I'm having that RAB position vector is 600 J. So I move from here like this. Okay, I move from here, point A, and I move down to this point. From point A, I move down to this point. Boom, that is 600 J. Then I come over to this place with respect to this distance. I come over to this place, I stop at B. That is, it is going opposite the coordinates. So to go like this, that is minus 450 I. From here, it moves like this, minus 450 I with respect to this coordinate. So that is minus 450 I. So if I rearrange it now, I have that RAB is equals to minus 450 I plus 600 J. Okay, minus 450i plus 600j. Alright, and then the next thing I'll look for is RAB modulus. Modulus of RAB, so the square root is minus 450 all square plus you have 600 all square. Right, so that is RAB equals to, so the square root of, if I find the square root, I'll be having, so 450 square gives me 202 500 plus, I'll look for this other one, 600. Okay, so 600 square will give me 360000. Now, of which if I add them, I'll be having RAB magnitude of RAB will be, okay, so this will give me 562 500. Okay, so if I find the square root now, I'll have the square root now will give me, okay, the square root will give me 750. That's the square root. The square root gives me 750. Okay, so I can then find lambda AB. It's a lambda AB, which is the unit vector. Unit vector AB will be equals to the position vector RAB all over the modulus of the position vector. Okay, so this now will be equal to 7, oh sorry, you write it out. Say lambda AB will be equals to, RAB gave us minus 450i plus 600j all over, this one is 750. Okay, so if I separate them, I'm having lambda AB is equals to minus 450i divided by 750 plus 600j divided by 750. Okay, so if I divide it now, I'll be having, I'll be having lambda AB 450, that will be minus 0.6i plus 0.8j. Okay, and then I can then look for the tension, the vector force, the vector of the tension TAB will be equals to tension AB times lambda AB, which is the vector TAB will be tension AB as lambda AB. And if you can recall vividly, we are told that the tension in cable AB is 6 kilonewton. That is about, tension in cable AB is 6 kilonewton. Okay, so I'll put it here in place of this TAB. I'll put it there, and then I'll be having, also put the value of lambda AB there. I'll have something like this. So by substituting now, I will have I'll be having tension AB vector. The vector force there will be in place of TAB, I write 6, open bracket, I put the value of lambda AB there, that is minus 0.6i plus 0.8j. And if I multiply now, I'll be having this, that vector TAB will be equals to, that 6 times this will give me, minus 3.6i plus 4.8j. Okay, which I can call this equation 2. Okay, so that is the value of vector TAB. The next thing I'll do there is to consider, consider cable AC. Let's consider the next rope. Consider the next rope, cable AC, and this will give me, okay, let's find the distance there. Okay, let's move from point A. I'll move upwards like this. Okay, bam, at this point that is 600G. Going up 600G, then I come down to C, come down like this with respect to this distance. Okay, if I come down like this, that is minus 320K. Okay, remember that K is going like this, but then this other one is coming down, so I move 600G and I come down like this, to this point to C. That is minus 320. Minus 320k. Okay, so I'll take that quickly. We're having that RAC will be equal to, that is 600 J minus 320k. Okay, I'll explain that again. Alright, so I moved again from here, from point A, I move up to this point, I stop 600 J, going up J, 600 J. Then from here I come down, that is minus 320k, because k is like this. If it's going like this, it's plus. So if it's coming like this, it will be minus. So coming down, that's minus 320k. Alright, so take note of that. Then I can then look for the magnitude. The magnitude RAC, magnitude of that vector will be equals to square root of 600 all raised to power 2 plus minus 320 all raised to power of 2. And this will give me square root of 600 raised to power of 2 is 360,000 plus and 320 raised to power. Okay, this will give me 102,400. If I add them now, have the square root of, this will be the square root of, if I add them, this will give me 462,400, of which when I find the square root of this answer will be, square root of this answer is 680. Okay, so this is the magnitude RAC, is 680. Now the next thing now I'll look for is lambda AC. I say lambda AC, which is my unit vector. Lambda AC will be the position vector RAC over the magnitude of the vector. Okay, so this now will be the position vector RAC. Remember we had RAC position vector as 600J minus 320K. So that is 600J minus 320K all over the magnitude of the vector, or the modulus of the vector, is 680. Okay, so if I divide that now by separating them, I'm having lambda AC, which is my unit vector. My unit vector will be equal to 600 J divided by 680 minus 320 K divided by 680. Right? Then I'll be having lambda AC. Lambda AC as if I divide that 600 divided by 680 will give me, okay, so this will give me 0.8824 J. Okay, and then when I divide that other one, that one will give me minus 0.4706 K. Okay, so I have lambda AC as 0.8824 J minus 0.4706 K. Okay, then I can then look for the tension TAC. Okay, the vector TAC will be equals to force TAC times lambda AC. Okay, so that is TAC times the unit vector lambda AC, and that will give me, okay, so this will give me TAC will be equal to, that is TAC times lambda AC was 0.8824 J minus 0.4706 K. So the vector TAC is equals to the force TAC times this. If I expand the brackets, so this vector now will be this times this, gives me 0.8824 TAC J minus 0.4706 TACK. Alright, and this now will be This is equation 3. Okay, that is equation 3. Then I can then consider, I say consider cable AD. Okay, let's consider cable AD. If I consider cable AD, I'll say let's look for the vector RAD. RAD, that is the distance RAD, and I'll be having, let's come back again to this, come back to the free body diagram. Now let's move from point A to point D. Let's see how we can get there. Now if I move from here, let's move, this is from here, go up to this point, that is plus 600J. From here I go up to this point, plus 600J, and then I come over to this place. Okay, take note of the distance. From here I come over to this place, that is plus 500I with respect to this 500. So from here I go like this, 500I. Remember that this is I coordinates. Okay, so from here like this I move plus 500I, and finally I go over to this place, which is minus 360. Is it minus or plus? Sorry. So if I go 500I, then plus 360K. Okay, so this is going like this. It's going like this. This one is going like this as well. The same direction with K. Okay, and this is the same direction with I. The same direction with I. Okay, so let's go again. Let's go. This is 600G, and then I come plus 500I, and then I go again plus 360K. Okay, so let's take that. So that means I'm having RAD as 600G plus 500I plus 360K. Okay, so take note of what I did. I moved from here, from point A, I moved upwards, that is 600G. Then I came over to this place. Okay, that is plus 500K. 500 from here, 500I with respect to the I coordinates, 500I, and then finally I go up again plus 300K this direction, 300K with respect to the K axis, 360K. I stop at point D. Okay, so this is it, 600G plus 500I plus 360K. So if I write them properly, I'm having that RAD equals to 500I plus 600G plus 360K. Okay, so that is it. I can then look for the magnitude of the vector. Magnitude of the vector RAD. Magnitude of this vector will give me, say, square root of 500 square plus 600 square plus 360 square. Okay, so this now will be RAD, which is equals to the square root of 500 square will give me 250,000. Okay, plus 600 square will give me 360,000 plus 360 square. 360 square will give me, this will give me, this is plus 129,600. So when I add them, I'll be having RAD is equals to the square root of, add them now, this will give me 739,600, of which when I find the square root of this now, the magnitude of the vector will be, okay, so using your calculator, 500 square will give us this, 600 square gives us this one gives us this one. So when I add them now, I have square root of 739,600, and the square root of that is what? 860. Okay, alright. Then the next thing I will look for now is lambda AD. Lambda AD will be equals to RAD over RAD modulus. Right? So this is lambda AD equals to RAD first there. The position vector is 500I plus 600G plus 360K divided by RAD modulus. The modulus is 860. Okay, so if I split them now, I'll be having something like this. Okay, so when I split them, I'll have that lambda AD is equals to 500I divided by 860 plus 600J divided by 860 plus 360K divided by 860. So I have lambda AD as this will give me if I divide this is 0.5814 I. Okay, plus when I divide the other one, that will give me 0.6976J. And when I divide this other one with my calculator, I'll be having 0.4186K. Okay, so that's the value. I can then impute it into half tension AD, which is equals to TAD lambda AD. Okay, so my tension AD is equals to TAD times lambda AD is 0.5814 I plus 0.6976G plus 0.4186K. Okay, alright, of which when I open that bracket, if I expand it, I'll be having something like this. Okay, I'll be having TAD equals to 0.5814 TAD I plus 0.6976 TAD J plus 0.4186 TAD K. Okay, so I have something like this. Alright, so I'm having this, so which I can call this equation 4. Alright, and the next one I look at is the weight. The weight of that body is acting vertically downwards, so it means that the vector W will be equals to minus WJ, of which I can call equation 5. Okay, so I have this. So you see that the weight is acting vertically downwards. That is why W is negative, minus WJ. Okay, that is. So I'll then substitute equation 2, equation 3, equation 4, and equation 5 into equation 1. If I substitute equation 1 now, I'll be having that the resultant arrow, which is sigma F, will be equal to, okay, so that will give me minus 3.6I plus 4.8j plus next. Okay, then I put equation 3. Equation 3 is 0.8824 TAC J minus 0.4706 TAC K. Okay, and I can then impute the next equation, which is equation 3. Equation 3 is equation 4. Equation 4 is 5814 TADI plus 0.6976 TADJ plus 0.4186 TADK. Okay, plus I put the next equation, which is minus WJ. Okay, that means that sigma F now will be, if I arrange all of them with respect to I, J, and K coordinates, take that of the first idea is minus 3.6. Okay, the next I is this other one, that is plus 0.5814 TAD. Alright, call this I, plus, let's take that of J. The first J I'm having is 4.8J. The next J here is 0. Plus 0.8824 TAC. Okay, and I take the next J, which is this, that is plus 0.6976 TAD. Right, then I take the next J, which is this one, minus WJ plus, okay, I take K, look for the first K, which is minus 0. That's this, minus 0.4706 TAC. Okay, I take the next K, which is this one, plus 0.4186 TAD. Okay, so I'm having this, having minus 3.6 plus 0.5814 TADI plus 4.8 plus 0.8824 TAC plus 0.6976 TAD minus WJ, and then plus open brackets minus 0.4706 TAC plus 0.4186 TAD close bracket K. Alright, and this is equivalent to sigma F equals to sigma Fx I plus sigma Fy J plus sigma Fz K. Okay, and that will give us, if I take each of them out, I'm having sigma Fx is equals to minus 3.6 plus 0.5814 TAD. Right, that's equation 6. Then sigma Fy will be equals to, I take this one out, 4.8 plus 0.8824 TAC plus 0.6976 TAD minus W, which I can call this equation 7. Then I say sigma Fz will be minus 0.4706 TAC plus 0.4186 TAD, of which I can call this equation 8. Alright, so I'll take the next equilibrium conditions. Next equilibrium conditions there is sigma fx equals to 0, sigma fy equals to 0, and sigma fz is equals to 0. It's a static equilibrium conditions. Static equilibrium conditions. Okay, so I'll apply it to equation 6, 7, and 8. And if I apply to equation 6 now, I have that sigma fx equals to 0, equals to minus 3.6 plus 0.5814 TAD. Okay, so I have this. I can call this one equation 9. Call that equation 9, and that will be this. And apply it to the next one, sigma fy. So that sigma fy now equals to 0. This will be equal to 4.8 plus 0.8824 TAC plus 0.6976 TAD minus W, of which I can call this one equation 10, and that sigma fz equals to 0. Fz equals to 0 will be equal to, this will be equals to minus 0.4706 TAC plus 0.4186 TAD, of which I can call this one equation 11. I have this as equation 11. Okay. Alright. So from equation Ix, that is, Ix is minus 3.6 plus 0.5814 TAD is equals to 0. I can make this subject of formula. I make this subject of formula. I'll carry this over here to become plus, and I'll have something like this. This is 0.5814 TAD equals to 3.6. Under tension AD, TAD equals to 3.6 divided by 0.5814. So tension AD now give me, so this will give me 6.192 kilonewton, and its tension in the rope AD. Tension AD is this. Okay, so I say substitute TAD equals to 6.192 kilonewton into equation Xi. Alright, so I'll be having, okay, I'll put this into this. I'll have something like this. I'll be having, okay, this is minus 0.4706 TAC plus 0.4186 TAD. It's equivalent to 0. Okay, so that will be minus 0.4706 TAC plus 0.4186, open bracket, put the value there, that is 6.192 is equals to 0. Okay, so if I expand this now, expand this distance, this will give me, I'll be having minus 0.4706 TAC plus, this will give me 2.59197 equals to 0. Okay, alright, so if I then carry this over here, I'll be having, that's a 2.59197 equals to 0.4706 TAC. So making subject of formula, I have TAC equals to 2.59197 divided by 0.4706 4706. And if I divide it now, I'll be having, if I divide this, I'll be having okay, so when I divide, I have 5.51 kilonewton, which is tension AC. Okay, that's the answer. Okay, so I've gotten the tension in cable AC as 5.51 kilonewton and tension in cable AD as 6.192 kilonewton. Alright. Okay, I say substitute the values of TAC and TAD into equation X. Okay, I'll write down equation X. Equation X is 4.8 plus 0.8824 TAC plus 0.6976 TAD minus W, okay, equals to 0. So what I'm looking for now is W. If I substitute the values, I'm having 4.8 plus 0.8824 times the value of TAC is 5.51 plus 0.6976 times the value of TAD. We had TAD as 6.192. Okay, that is times 6.192. Okay, if I multiply, I'll be having something like this. This is 4.8 plus, if I multiply this now, I'll have to give me 4.862 plus, if I multiply this to, I'll have, this will give me 4.319 minus W is equals to 0. Right, 4.319, I multiply this, minus W equals to 0. So I'll then add everything and I'll have, okay, this is it. I'll quickly add this and then I'll get something like, so I'm having 13.981, okay, minus W is equals to 0. I carry this over here. I'm having 13.981 equals to W. So therefore, the weight is equals to 13.981 kilonewton. Okay, so I've gotten the weight of that body as 13.981 kilonewton, and I also had the tension AD, tension in cable AD as 6.192, and then I had tension in AC as 5.51 kilonewton.